Hey there! Today we're diving into the fascinating world of data representation in computers. Computers are amazing machines, but they don't think like us. We use languages like English, but computers use binary code. Data representation translates our information into a format computers understand. Imagine teaching a robot to bake a cake. You need to break down the recipe into simple steps and symbols. That's what data representation does for computers. It converts our words, numbers, and images into a language computers can digest. In this digital age, we're constantly surrounded by data. From text messages to videos we watch, it's all data processed by computers. Understanding data representation unlocks the potential of these machines. So buckle up as we explore data representation in computers. At the heart of it all lies the binary system. It's a number system that uses only two digits, 0 and 1. Think of a light switch. It can be either on, 1, or off, 0. That's binary in a nutshell. Each 0 or 1 in binary is called a bit, short for binary digit. And just like we combine letters to form words, computers string together these bits to represent all sorts of data. A group of 8 bits is called a byte. Now you might wonder, why use such a simple system? Well, computers are built on electronic circuits, which can be either on or off, just like our light switch. Binary's elegance lies in its simplicity, perfectly matching the on-off nature of electronics. Every number, letter, symbol, and even instruction that a computer processes is ultimately broken down into a unique sequence of binary digits. It's the fundamental language that bridges the gap between human communication and the intricate workings of computers. Working with long strings of zeros and ones can get pretty messy for us humans. That's where the octal system comes in handy. OCT means 8, and in the octal system we use 8 digits, 0, 1, 2, 3, 4, 5, 6, and 7. The beauty of octal is its direct relationship with binary. Each digit in octal represents a group of 3 binary digits. For instance, the octal digit 2 is equivalent to the binary sequence 010, and 7 in octal translates to 111 in binary. Octal provides a more compact way to represent binary numbers, making them easier for humans to read and write. It's like using abbreviations instead of writing out full words. It saves space and makes things less cumbersome. Section 4, Hexadecimal, a more compact code. As our use of computers grew, we needed an even more efficient way to handle binary data. Enter the hexadecimal system, or hex for short. Hexa means 6, and deci means 10, so hexadecimal uses 16 digits 0 through 9 plus A, B, C, D, E, and F to represent the numbers 10 through 15. Hexadecimal is like the ultimate shorthand for binary. Each hexadecimal digit represents a group of 4 binary digits. For example, the hexadecimal digit A is equivalent to the binary sequence 1010. This makes hexadecimal even more compact than octal, allowing us to represent large binary numbers with fewer digits. Think of it like this: if binary is like spelling out every single letter of a word, hexadecimal is like using acronyms. It's a concise and efficient way to represent large chunks of binary data. This is especially useful in programming, where we often deal with long binary strings. Section 5, Fixed point, representing fractions. Let's talk about representing numbers with decimal points. One way is using fixed point representation. Imagine a ruler with a specific decimal point. Numbers to the left are whole numbers, to the right, fractions. In an 8-bit fixed point, 10.5 is 1010.1000. The first 4 bits are 10, the last 4 0.5. Fixed point is simple to understand and implement, but it limits the range of numbers it can represent. Section 6. Floating point, handling very large and small numbers. To overcome the limitations of fixed point, we use floating point representation. This method is similar to scientific notation, where we express numbers in terms of a mantissa and an exponent. In floating point, the mantissa represents the significant digits of the number, and the exponent indicates the scale or magnitude. For example, the number 123.45 can be represented in scientific notation as 1.2345 times 10 to the power of 2. In floating point representation, we would store the mantissa, 1.2345, and the exponent, 2, separately. This allows us to represent a wide range of numbers, from very small to very large, with a fixed number of bits. Floating point representation is more complex than fixed point, but it provides much greater flexibility and precision. This is crucial for applications that require high accuracy, such as scientific simulations, financial modeling, and computer graphics.